Chapter 6, the normal distribution. Alright, so last unit we talked about our random variables. We talked about discrete random variables and continuous random variables. We specifically talked about probability distributions in the last chapter for discrete random variables. Well, in this chapter, we're talking about probability distributions for continuous variables. A couple things we need to know. The area under the curve for your continuous random variable or your probability density curve is equal to 1. And then we can look at the area between two values to find the specific probability or proportion of values that fall between those two values. Alright, so the drawing on the left shows an example of what a probability density curve looks like. This is not what all of them look like. This is just like an example. They're curved out. And again, you have a total probability underneath of 1, and then you can look at specific values or specific probabilities between two numbers. In this case, we're looking at values between 4 and 6, as shown by the highlighted blue area in the picture. Alright, so it says, what is the proportion of the population, or what proportion of the population is between 4 and 6? Well, the proportion is equal to the area under that section of the curve. And so they told us in the drawing that the area was 0.16. So that means the proportion of the population between 4 and 6 is equal to 0.16. If we want to know the probability that the number or that people or part of the population is not between 4 and 6, I would simply do 1 minus 0.16. Again, since the whole curve equals the 1, the entire probability equals 1, I can do 1 minus 0.16 to get the proportion that is not between 4 and 6. So if I do 1 minus 0.16, I get 0.84. Alright, so here again is what our standard normal curve looks like. Our standard normal curve is centered at 0. In other words, it has a mean of 0, and it has a standard deviation of 1. We talked about z-scores in the past, and basically your z-score tells you the number of standard deviations above and below your mean. So in this case, we're looking at the number of standard deviations above and below 0. If it's below 0, then it has a negative z-score, and if it's above 0, it has a positive z-score. Alright, suppose we want to find the area to the left of 1.26. What I would do first is I would draw out that curve and see what it looks like. I draw out 1.26, which I know is to the right of 0. I shade everything to the left of it. Alright, now I have two options. I can either use table A, which is your standard normal table. You can find that in your book, or you can simply do a Google search for a standard normal table, or you can use technology. I'm going to show you both ways. Alright, so starting with table A, what I would do is I would look along the left-hand side to find 1.2. Since the z-score value that we're looking for is 1.26, I start by looking for 1.2. And so here, right here, this highlighted yellow row represents everything for 1.2. Now, since I want 1.26, I look for 0.06 across the top, which is right here, and I highlight that row yellow. Wherever those two rows intersect, that's my probability. So the area to the left of 1.26 is going to be 0.8962. Now the key thing to remember is that your standard normal table only gives values to the left. If this question asks to the right, that would not be my answer. But since it asked for to the left, whatever the table gave me, that is my answer. So again, 0.8962. I could also use my calculator to figure out that answer. So what I would do is I would hit second vars, which should say distribution. So again, second vars. I would scroll down until I see normal CDF. I do not want to click PDF. I want normal CDF. When you click normal CDF, the way you put this in is you do your lower bound, which in this case, since we want everything to the left of 1.26, the lowest possible number is going to be down here, which is negative infinity. The way you type in negative infinity in your calculator is you do negative 1 E99. Alright, so that's my lower bound, comma, then you put your upper bound. What's the highest number you have? Well, in this case, the highest number we want to go to is 1.26. All right, so again, lower bound, comma, upper bound, and then you do comma, your mean, and your standard deviation. Remember, because we're dealing with z-scores, which is a standardized value, the mean and the standard deviation is 0 and 1 respectively, every single time. All right, so again, lower bound, upper bound, mean, standard deviation. I plug that in with commas, and I press enter, and I get a probability of 0.8962, just like my table. All right, so next example, it says find the area to the right of z equals negative 0.58. So again, I'll start by drawing my little picture so I can just get a visual of what I'm looking for. Negative 0.58 should be slightly to the left of 0. Again, I can use table A or the standard normal table. What I would look for on the left-hand side is a z-value of negative 0.5. And then across the top, I'll look for 0.08. Again, where that column and that row intersect, that's my answer to the left. So this 0.2810 is the area to the left. In other words, this white area is what it's telling me. The area to the left of that z-score value. So the way that I'm going to find the area to the right, since the total area is 1, I do 1 minus 0.2810, which is 0.7190. Again, in my calculator, I can do the same exact thing. This time, my lower bound, since I'm going to the right, my lower bound is going to be negative 0.58. My upper bound, or the very highest point that I want, is going to be infinity. So I type that in as 1e99 with the mean and standard deviation of 0 and 1. Press enter, it gives me 0.7190, the same thing I got when I calculated it out using my table. Notice that the calculator, you don't have to do 1 minus that. Whatever the calculator gives you is the answer because you specify to the calculator the lower and the upper bound. All right, last example for standard normal tables or standard normal curves. We want to find the area between z equals negative 1.45 and z equals 0.42. So again, sketch it out. We're not going to infinity this time. Notice we have bounds on both ends. I could use my standard normal table, but this time I have to find the values for negative 1.45 and 0.42. So if I do negative 1.45 on my standard normal table, I get 0.6628. And if I do it for 0.42, I get 0.0735. To actually calculate the probability between those two values, I simply subtract them. So 0.6628 minus 0.0735 to get a final answer of 0.5893. Now for me, the calculator is a little bit easier. So what I would do is I'll type in normal CDF, my lower bound, negative 1.45, comma my upper bound, which is 0.42, comma mean 0, standard deviation 1, and I get the same answer. Notice that the answer is a little slightly off. But just keep in mind the calculator is giving you the actual more accurate answer. So depending on whether you use the calculator or whether you use the table, your answer will be slightly different, but Connect Math will take either answer. All right, last thing is we need to figure out how we can find a z-score that corresponds to a particular area or probability. Here's some, like a little bit of a different notation. If I have the z and then like a little underscore alpha, that's basically asking for the z-score that corresponds to that alpha, where alpha is the area to the right. All right, so again, I can use the standard normal table, but again, that's going to give me the area to the left. So what I'd like to do is I just prefer to use the calculator. But when I use the calculator, I have to remember that my calculator for this will also only do to the left. All right, so the first thing I do, if I have an example like z of 0.20, they're asking me for the z-score that corresponds to the area to the right of 0.2. I would type in the same button, second vars or distribution, but this time since I'm looking for the z-score and I have the probability or the area, I type in inverse norm. Now when you type in inverse norm, you have to type in the area to the left. So if the area to the right is 0.2, then the area to the left is 1 minus 0.2, which is 0.8. And then you type in your mean and your standard deviation of 0 and 1. Alright, so when I type that in, press enter, I get 0.8416. In other words, this z-score that corresponds to 0.2 to the right is 0.8416. 0.416. That z-score also corresponds to 0.8 to the left. Alright, so just a quick review. You guys have seen this formula before. This is your z-score formula. Your z-score formula simply says to take x, or whatever value you're looking for, minus the mean over the standard deviation. The z-score again tells you how many values above or below the mean you are, how many standard deviations above or below the mean you are. Alright, so for example, it says heights in a certain town of women follow a normal distribution with mean 64 inches and standard deviation of 3 inches. A randomly selected woman has a height of 67 inches. Find and interpret the z-score. So for this lady, we're going to take our z-score formula. X is going to be 67. We're going to subtract off the mean of 64 and divide by our standard deviation of 3. 67 minus 64 is 3. 3 over 3 is 1. That means that the z-score is 1. This is simply saying that a woman that is 67 inches tall is 1 standard deviation above the mean height of 64 inches. In other words, she's taller than most. Here's another example. A study reported that the length of pregnancy from conception to birth is approximately normal, with a mean of 272 days and a standard deviation of 9 days. What proportion of pregnancies last longer than 280? Now again, they told us in this problem that it was normally distributed. So that tells us that we can use the normal CDF button in our calculator. As long as they let us know it's normal, I can use that normal CDF button. So again, it says what proportion of pregnancies last longer than 280 days? Well, 280 days would be my lower bound. Since I want longer than that, it would be 280 to infinity. Alright, so when I put it in my calculator, I do normal CDF, 280 as my lower bound, 1E99 as my upper bound, my mean of 272, and a standard deviation of 9, which gives me 0.1870. Or to answer the question properly, we could say the proportion of pregnancies that last longer than 280 days is 0.1867 or 18.67%. Alright, going right back to that same example, this time I'm asking if a pregnancy is considered to be full term. It has to be between 252 days and 298 days. What proportion of pregnancies are actually considered full term? So again, this time I'm giving you a lower and an upper bound. So, and we know it's normally distributed. I can use normal CDF, lower bound of 252, upper bound of 298, mean of 272, and standard deviation of 9. Plug that in, we get about 98.5%. Just to conclude in a nice sentence, I would say the proportion of pregnancies that are full term, which is between 252 days and 298 days, is 0.9849 or 98.5%. All right, another example. Mensa is an organization whose membership is limited to people whose IQ is in the top 2% of the population. Assume that the scores on the IQ tests are normally distributed, with a mean of 100 and a standard deviation of 15. What minimum score is needed to qualify for membership into Mensa? Alright, so this time I'm giving you, if you notice, the area. I'm telling you the proportion. I'm telling you that probability is 0.2. Alright, but notice I'm giving you the top is 0.2. That means the bottom or the left-hand side is 0.98. So, sorry, I think I said 0.2, but it's 0.02. So the top is 0.02, and then the bottom would be 0.98. So since I'm looking for the actual score, I'm not looking for the area this time. They gave me the area. I'm looking for the score. I need to use inverse norm. So in my calculator, I'll type in inverse norm. I want the area to the left, which is 0.98, with a mean of 100 and a standard deviation of 15. And I get 130.806. And I would interpret that as the minimum score needed to qualify for membership in Mensa is about 131. All right, next we're moving into what we call sampling distributions. It's essentially the same thing that we've been doing, but this time instead of looking for a value or one value, we're looking for the value for a sample. If we're specifically talking about sample means, like we have a whole bunch of sample means and I want to know the average sample mean or the standard deviation of the sample means, well, your mean of your sample means or your mean of your sampling distribution is just the mean of the population. So mu equals mu. The mu of the sample means equals the mu of the population. If I'm looking for the standard deviation of the sample means, the standard deviation of the sample means equals the standard deviation of the population over the square root of n, where n is your sample size. Keep in mind that your standard deviation is also sometimes called your standard error. Alright, so example, it says among students at a certain college, the mean number of hours of television watched per week is 10.5 and the standard deviation of 3.6. A simple random sample of 16 students is chosen for a study of viewing habits. Let X bar be the mean number of hours of TV watched by the sample students. Find the mean and the standard deviation of the sample. Alright. So the mean of X bar is just the mean of your population. So your mu X bar is just your mu of your population, which they gave us in the problem of 10.5. Your standard deviation of X bar, or your sample means, is simply a standard deviation of your population, which was 3.6, over square root of n. Your n is your sample size, which is 16. So I'll do 3.6 over the square root of 16, which is 0.9. Now, that's all well and good, but the whole point of this is actually to be able to calculate probabilities. Well, we have a really nice theorem that was used all over statistics called the central limit theorem. The central limit theorem basically says if your sample size is greater than 30, then we can approximate the distribution to be normal. Well, if we can approximate the distribution to be normal, then we can use stuff like normal CDF or the standard normal table, table A, to calculate probabilities. So your ultimate goal is that you want to make sure that the sample is greater than 30. You want to make sure that it's normally distributed so that you can actually calculate the probabilities and you get to find useful information. Alright, so here's an example. It says, based on the data from the U.S. Census, the mean age of college students in 2008 was 25 years, and a standard deviation of 6.8 years. A simple random sample of 64 students is drawn. What is the probability that the sample mean age of the students is greater than 26 years? So the first thing that stands out to me is that we have a simple random sample of 64 students. 64 is greater than 30. So by the central limit theorem, we can approximate this distribution normal. Again, it's basically all it's saying is as the more students that we have, or as we increase our sample size, it gets more and more normal. 64 is way above 30, so we can approximate this normal for sure. And if we can approximate the normal, then we can use normal CDF to calculate the probability that they're actually asking for. Alright, so what I'm going to do first is I'm going to find my mean. Remember, your sample mean is just equal to the mean of the population, which is 25 years. And then your standard deviation is your standard deviation of the population over the square root of n, or in this case 6.8 over the square root of 64, which is 0.85. Once I have that, and again, because it's normal, because I know that my n is greater than 30, I can do normal CDF in my calculator. And remember the question, they're saying that they want to know the probability that the student is greater, or the sample mean age is greater than 26 years. So we have 26 as our lower bound, infinity or 1e99 is our upper bound, with a mean of 25 and the standard deviation we just calculated at 0.85. Plug that into our calculator, we get 0.1197, and that basically just says that the probability that the sample mean age of a student is greater than 26 years is approximately 0.1197 or 11.97%. We can do the same exact thing for proportions. We can calculate the mean and standard deviation of sample proportions. The mean of our sample proportion is equal to the proportion itself, and that is the proportion of success. P equals a proportion of whatever you're talking about in the problem. It's the proportion of successfully doing whatever you're talking about. And your standard deviation of your sample proportions is the square root of P times 1 minus P over the square root of n. In other words, it's the square root of your proportion of success times your proportion of failure divided by n. Alright, so example, it says The soft drink cups at a certain fast food restaurant have tickets attached to them. Customers peel off the tickets to see whether they win a prize. The proportion of tickets that are winners is P equals 0.25. A total of N equals 70 people purchase soft drinks between noon and 1 p.m. on a certain day. Let P be the proportion that win a prize. Find the mean and standard deviation of P hat. Alright, so your mean of P hat, or your sample proportions, is just equal to your proportion of success, which is 0.25. Your standard deviation of your sample proportions is equal to your proportion of success, which is 0.25, times your proportion of failure, which is 0.75, or 1 minus 0.25, over N, which is how many people were part of the study, in this case 70. When I plug that into my calculator, I get 0.0518. Alright, so we also have the central limit theorem, or what they call the central limit theorem for proportions. Remember, for means, it has to be greater than 30, your sample size. This time, for proportions, you have to take your sample size, multiply it times your proportion of success, and you also have to take your sample size and multiply it times your proportion of failure, and both of those have to be greater than or equal to 10. If they're both greater than or equal to 10, well, then we can approximate the distribution to be normal. And if the distribution is normal, again, we can use items like the standard normal table or normal CDF in our calculator to calculate probabilities. Alright, so what we're going to do is we're always going to check to make sure that we can approximate it normal. If we can, then we'll use our normal curve. We'll find our mean and our standard deviation, sketch our curve out to kind of get a visual, and then use either table A or our calculators to calculate the probabilities. Alright, so last example. According to Summit Entertainment, 80% of the audience for the opening weekend of the movie Twilight, the Moon, was female. If a random sample of N equals 100 members of the audience were sampled, what's the probability that the sample proportion of females would be greater than 0.85? So first thing I need to do is I need to make sure that this thing is even normal. So I'm going to check NP. N is 100, and my P, proportion of success, is 0.8. 100 times 0.8 is 80, which is definitely greater than 10. And then I also have to check my proportion of failure. So I do N, which is 100 times my proportion of failure, which is 1 minus 0.8, which is 0.2. 100 times 0.2 is 20, which is also greater than or equal to 10. Because both of them are greater than or equal to 10, we can use the normal curve. So with that being said, I'm going to go ahead and find my mean of my proportions, my standard deviation of my proportions. The mean of my proportion is 0.8, which is given in the problem. Remember, it's just the proportion given. And then my standard deviation of my sample proportions is P times 1 minus P over N. Plugging in those numbers, I get 0.04. Next, I can sketch out my curve. Again, we're looking for the proportion that will be greater than 0.05. And then if I use my calculator, I have normal CDF, 0.85 to infinity, comma, mean 0.8, and standard deviation 0.04, and I get a final answer of 0.1056. In other words, 10.56% of the females or whatever would be greater than 0.85.